Welcome back. This is a continuation of a previous exercise where we're looking at how to construct a multiple regression. We use data from on territory sales. We predicted territory sales using advertising, sales reps, and WEI. So here's where our last video stopped. We were looking at how you can examine relationships specifically using multiple regression. In this particular exercise, we examined the role of advertising, sales reps, and WEI on sales. We conducted this analysis by constructing a multiple regression. So what we did was we essentially ran some analysis that gave us this output. We got the output by running regression linear and moving our predictors to independence and our outcome variable to dependent. We also checked the box for collinearity diagnostics to get VI values for every single independent variable. When we ran the analysis, we got the following output. The output showed us the following things. It showed us a couple of things, including we saw overall R squared of our model was 0.881, which because the R squared value has a F statistic and P value under 0.05, led us to conclude this R squared value of 0.881 is statistically significant. We then went on to examine individual predictors, learning from the coefficients table that each of these predictors, well, two of the three predictors are significant and the third one isn't, which then we went on to write out a regression equation, including the two significant variables. A lot of what's in the coefficients table focuses on inference. In this section, we're going to talk more about prediction. Now, some of the prediction part we've already examined before in the prior video, the part where I highlighted the magnitude of the R squared. So not only was our R squared statistically significant, but it was a large R squared. Now, if the R squared was not significant, you wouldn't even think about how large it is or how small it is, because inferential statistics told you that it is not significant, and that's that. In our case, we're not going to look at, well, how large is R squared? We'll turn to heuristics for R squared that tell us that an R squared above 0.50 or 0.5 is a strong model. Between 0.5 and 0.1 and 0.5 is moderate, under 0.1 is weak. Thus, we have a strong model. So based on R squared, our model is strong. Now, this would be a good time to take a step back and talk a little bit about where R squared came from. For that, I'm going to take you back a couple of slides to a bit about the intuition or theory behind R squared, where that came from. So let's go back a couple of slides. And in a prior video, I talked about a relationship between two variables we examined part of a research project. The scatter plot gave us this picture, and when we fitted a baseline model, we got this. Regression line gave us a best fitting line that went through the data as follows. The R squared index as such is simply a comparison of the regression model to a baseline model. The regression model is clearly not going through all the points out here. Thus, the regression model has some level of error associated with it. Simply adding up the deviations below the line and above the line will give us a 0. Because regression model is designed to fit the points as best as possible so that deviations above the line and below would cancel out. Therefore, to construct an index of regression model error, we need to square all the errors and sum them. This gives us a measure of sum of squared errors. In SPSS, this is referred to as sum of squared residuals. Now, if you do the same exact thing for the baseline model, you would get sum of squared total. R squared is basically a comparison of the regression line to the baseline. The number that identifies the error for regression line is sum of squared residuals in SPSS. or we also know it as sum of squared errors, or SSE. The total sum of squares is noted or identified by the green line, which is the number error for the baseline model. Let's connect the dots now by going to SPSS. We're going to then find what SSE and SST are and figure out how this formula relates to R squared. Let's go over to SPSS now. Within SPSS, you'll note we have a table called the ANOVA table. In here, there is a measure of sum of squared errors or sum of squared residual. If you compare this number to the total, you'll get your R squared based on the formula listed in the slide. Specifically, 1 minus of the residual sum of squares or sum of squares error divided by sum of squared total will give you this number R squared. The reason I went through that exercise was to identify or highlight the fact that our R squared value is derived from the errors in our regression model. In fact, all measures of prediction are in some way derived from the errors in your regression model. They somehow quantify the error values you saw in the regression model. The R squared as such is many folks look at the R squared and think of it as being theoretical. While there's some truth to that, we'll get to more of that in a later session. The R squared as such is a nice index because it ranges from 0 to 1. So many folks like the fact that you can think of the R squared in terms of percentage. Now, the problem with the R squared measure is that it is unitless. It is like a percentage measure or an index from 0 to 1, and it doesn't have a direct. It's not in the units of the dependent variable or outcome variable. An R squared of 0.881 does not mean that we are 88.1% correct in predicting what sales is. And that's sort of the reason why we're going to look at two other measures of regression. And these are RMSE and MAPE. That's a mouthful. RMSE stands for root mean squared error. There's that mouthful I was talking about. MAPE is mean absolute percentage error. What we're going to do now is compute these metrics for our models. Now, the key point to note here is both models have an E in them, or both metrics have an E in them. That's the error part. Let's go and figure out where this error comes from. In the slides are some instructions we're gonna follow to get that error value. Specifically, when running a regression, we're going to request our unstandardized predicted values and unstandardized residuals. Our next step then would be to go back to SPSS. We're going to run our regression. We already have our independent variables in here and our dependent variable. We also have the collinearity diagnostics checkbox checked. Okay. What we're going to do different now is we'll click on the Save button, which will give us the unstandardized predicted values and unstandardized residuals. Having checked those two boxes, we can now rerun the analysis. If you look carefully at the output from running this regression analysis, the output is pretty much the same. The only additional information is we have a box of residual statistics. Now, if you look at this table, you'll note something very interesting. We have a row for residual in here, and bear in mind, residual is the error. Those are the drop lines you saw in the graph from the regression line to the data points. It's telling us that for some residuals, for some observations, the residuals were large, and for them they were well, small. The range was -87 to 76.6927. Now these numbers are in the units of the dependent variable. In other words, you can tell by looking at this that the biggest error on the downside for your regression line was -87. You're off by, underestimated by 87. And the other one is 76, is sort of like the opposite type of error. I'm sorry, -87 would mean you overestimated. 76 would mean you underestimated. If you were to combine all those error values, the average of those error values would be 0. You'll recall the regression line is optimal because it fits the data in such a way. If you added up all of the errors, you'd get a 0. If you average, of course, if the sum is 0, you'd also get an average of 0. Okay. Now, having done the analysis we just did in SPSS, we get more than just this table of residual statistics. What's most important is we get a table of, let's go to data view now. Let me find the data view here. I can't find it on my screen right now. Okay. So here's our data view. And you go to the data view, you'll see now we have 2 new columns added on. Pre-1 and Res1. So Pre-1 are the unstandardized predicted values. Res1 are the residuals. If you look at this table, you'll notice that for any given value of sales, we have predicted value and the difference between the predicted value and the true value. So for the first one, our true value for sales was 260, and Pre-1, or our predicted value based on our equation, is 265. Res1 is -5.52, and so on. So for example, third observation, the true value is 279.4, our prediction is 267, and our difference in those values is 12.13. So you kind of see out here, if you go through this list, some numbers in the rest column will be positive, some would be negative. If you were to add up the numbers by, let's say, doing analyze descriptive statistics, frequencies, and then you were to sum all the unstandardized residual values. Okay. I'll uncheck the box for frequency tables because we don't want that. We only want the sum of the unstandardized residuals. If you did that, you'll notice that this is exactly 0. Okay. So for our 40 territories, the sum of the residuals is 0. And that's what regression is designed to do. So it's doing what it's supposed to do. All right. So we have here a column called Pre-1, a column called Res1. What we want to do now is compute our RMSE. Let's take this apart. That's root, mean, squared, error. We already have the error. Let's then do the squared error part. So we're going to do the SE of the RMSE. We'll do this by creating a column called SE. Transform compute variable enables us to create new variables. Here we are. So in target variable, we'll say SE for our new variable. Our new variable is simply the square of our residual. In SPSS, square is denoted with a star 2, and then the exponent. Okay. Hit OK, and now you've got a new column in your data view called SE. Let's verify this math is correct. -5.52 squared is 30.53. -65 squared, I don't know what that is, but I'm guessing it's around 4,000 or so. That number sounds about right. Okay. we already know that if you square a negative number, you get a positive number. And that's part of the reason why we love to square. Statisticians love to square numbers because it takes away the negative sign. So now we've got the SE of RMSE. That's good. Let's now work on our second metric. We'll work on the RM of SE a little later. Let's go and look at our second metric, which is MAPE. This stands for mean absolute percentage error. We already have the error. Let's now figure out the absolute percentage error. Given a number like minus 5.52, you can figure out the percentage error. So the percentage error would be, in this case, minus 5.52 divided by the true value times 100. Times 100. This would be our percentage error for the first observation. If you want to take the negative sign away, you can apply an absolute value function to this. So we're going to compute for every single residual, or from every single residual, we'll compute the absolute percentage error, or APE. To do so, we'll do the following. Transform compute variable. We'll go to target variable APE, short for absolute percentage error, and apply the logic I just went over with you. So residual divided by true value, which is sales, and multiply this thing by 100, and we'll wrap this whole thing up the absolute value function. You can find functions in compute by looking under the function group and identifying the relevant function. The little callout, the little box here shows you the structure of that function. So go here, ABS, and put this whole thing inside the ABS. When it comes to computing or doing transform compute, SPSS doesn't care about white space, except for variables, variable names, it doesn't care about case. For example, your function could be lowercase or uppercase, it wouldn't matter, but rest one would have to be the same case as the actual variable name. You can't mess with that, the case for that variable. Okay, you hit OK now, you'll get another column called APE. We now have two new columns, one called SE, one called APE. Let's go on to our our next letter in the abbreviation. So the first one, SE here is RMSE we're doing. So we want to get to RMSE. So we already have SE. What we want to do next is do the M part for both columns. The M part is the mean part. That is, how do you figure out the average for these columns or mean for these columns? So if you compute the mean for this column and mean for this column, you'll get MAPE and MSE. Let's do that. Analyze, descriptor statistics, frequencies, and now I'm going to bump, I'll reset this screen. I'll move SE and APE out to the right, specify statistics as being mean, uncheck the box for frequency tables. If I leave this box checked, we'll get a lot of garbage output, and I don't want us to have a lot of garbage output to look at, so uncheck that box. Hit OK. Now, in the output window, we have the MSE and MAPE. So the the MAPE, this would be MAPE, rather, let me do it correctly here. Just down here. would be the MAPE, and this here would be the MSE. So our MAPE is 8.56. Our MSE is 1776. Let me pull out my calculator and figure out what the RMSE is. RMSE would be the square root of MSE, which would amount to square root of 1776. Nice number, 1776. Huh? 09. And if you run that square root, you'll figure out the square root is 42.14378. So let me head back to the slide now. We can put all these numbers together. Our RMSE turns out to be 42.14378. MAPE is 8.5622. All right, now that's good. As we, in the lead up to this point, I noted that R squared does not have a unit. Well, that naturally means since we're doing RMSE and MAPE, these should have a unit. Okay, so what is the unit for RMSE? Well, RMSE does the same unit as the dependent variable. So it's thousands of dollars. So RMSE in our case can be interpreted as being $42,143.78. So on average, we're saying for any given prediction about sales, we're off from the real number by $42,143. The MAPE is a percentage number because it stands for mean absolute percentage error. So on average, for any given territory sales, our prediction is off from the real number by 8.5622%. As you can tell, these have a better ring to them to somebody who's solely interested in figuring out if their sales are, hitting the mark, how good the model is for predicting sales. Right? Okay, so RMSE again is $42,143, and the MAPE is 8.5622%. I want to highlight one more thing before we move on, which is that when you construct your residuals and predicted values columns, we had a res1 and a pre1 variable showing up. If you rerun the analysis, your new columns will be called res2, pre2. When that happens, you may have to adjust your compute variable accordingly. Okay. Specifically, let's take a look at what happens if you were to rerun this analysis. Let's say I decide to go analyze regression linear, repeat the same exact step. Okay. Now we have two new columns that are called pre2 and res2. You want to be aware of this because now if you go to compute the MAPE or the MSE, you want to make sure that you're using the correct res variable. Okay. All right. So that's what we had for two more. We've examined this in this video, two more metrics for computing how good your model is or how good the prediction quality is. Thank you for joining me.